So hi everyone. So thanks for coming out to another Stellar Society lecture. We've been doing this since 2010 as a spring event, and for many years we've had it aligned with the North Carolina Science Festival. And welcome to the last weekend of the 2025 North Carolina Science Festival. How many of you have been to an NCSF event already this month? Good for you. So if you don't know about the Science Festival, every April, North Carolina just goes science crazy, and there are events all over the state, and they're open to the public and all ages and all disciplines. And it's a fun time here in North Carolina to just do science and have fun doing science. We host a few such events here. We have a Science Hall open house. We participate in the statewide Star Party, and we have this event. But there are a few more days left, so if you look up just Google the North Carolina Science Festival, you can see what the upcoming dates are. And mark your calendars, April will come back around next year, and there will be more such events. We have some of the festival organizers here with us today, so we're glad they came to see tonight's talk. It is cloudy tonight. We don't expect to have our regular Friday viewing session, so that's okay. We've got a great event that can hold your attention for the next hour or so. And you can always come back. We're open every clear Friday night all year long. Start these days as darkness falls, so that's going to change as the summer goes on. And then during winter hours, we start at 7 o'clock. But if you haven't been out, come out and look through our telescopes. We love showing the universe to you. I would like to thank a few people before we get started. As always, the GTCC Foundation helps support our public outreach events, and the persons who donate to the observatory funds to help do that. Thank you all so very much for doing that. If you're interested in donating, if you find the Klein Observatory website, you can find the Support the Observatory page, and there will be places where you can contribute, and we would appreciate it if you did. All our events are free, and so we make sure that there's no impediment for people to come out and share the universe with us. So support us if you will, either through your donations or through just coming out and looking through telescopes and attending our events. Also like to thank, as always, the Martin family here in the front row. I've worked here for 24 years as director of the observatory, but I wouldn't have such a great job if it weren't for Aaron Martin, who was my predecessor. He and Ruth and Tim, who are here, helped to really get this program off the ground and literally built the observatory here on our grounds. And their philosophy was our philosophy that the universe should be open to everybody. And so we're appreciative of their efforts. And we can't do weekly observing programs without lots of volunteers, because Steve Desch, who's right over there, and I are the astronomy faculty, but we really need help. So we've got a lot of trained volunteers, some of whom are students who came through our programs, and I see a few of them there wave at us. And so they, if you come out on Fridays, they'll show you the planets, the moon, the star clusters, the galaxies, the double stars, the whole 9 yards. So thanks again for coming out. So I don't want to talk too long about all of that, but let me do a couple of housekeeping things. If you are in somebody's class here for credit, you should know what you're supposed to do. If you're a Guilford Tech student, there's a little box in the lobby where you'll dump something off or you'll give it to me. If at the end of the talk we're going to have some question and answer, so if you think you really need to leave right away as soon as the talk ends, please go out the back doors and down the back stairs rather than rushing the front where people are trying to hear questions and ask questions. So let me get things rolling for tonight's talk. We heard a story recently about a graduate student at UNC-Chapel Hill who had found the youngest ever exoplanet found, and we thought that was really cool. And so I wrote her a while back and said, hey, can you come to our TriStar event, which is something we have in March, but she couldn't do it. And I didn't give up, and I asked her, what about April? And so here she is, Madyson Barber, who is a PhD student at UNC-Chapel Hill. She works with the Young Worlds group under Dr. Andrew Mann, and that's a relatively new group at Chapel Hill, and they're doing really interesting work on planets around other stars, and especially very young systems, trying to figure out how these systems form. And so she's going to tell us about that work tonight. She's well decorated, even from her undergrad years. She won several recognitions, Space Grant Award, you were a Chancellor's Award person, so she's been recognized for her good work and snapped up into this team where she's done some really exciting work with the TESS mission and looking at the exoplanet data there and finding out some really interesting things, and she's going to tell us about that tonight. So let me turn things over to Madyson Barber.
Hi, everyone. Just to quickly reintroduce myself, my name is Madyson Barber. I am a graduate student at the University of North Carolina, Chapel Hill, where I work with Dr. Andrew Mann and the Young Worlds Lab. And I primarily work on the detection and characterization of young transiting systems using test data. Oh, that's a mouthful. Really, what my little tagline is I'm a planet hunter. I look for young transiting planets in order to better understand how planets form and evolve. So if you're to ask me what I think, maybe. Okay, there you go. If you were to ask me what I think that a lot of astronomers are interested in, I think all of us boil down to similar questions. Answering questions regarding, are we truly unique in the universe? Where do we come from? Where are we going? The big picture questions of where do we fit into this giant universe that we call home? And so our little pocket of astronomy focuses on discovering planets in order to understand planet formation and evolution, to really understand how did the Earth form and what is the Earth evolving into. And so, okay, I don't think the clicker's going to work. But in order to understand the science that we're doing now, we have to understand the science that's already been done. So there's a lot of debate over what we consider to be the first exoplanet. And then rather than picking a side, I've decided to offer you 3 choices for what you might consider to be the first exoplanet. So in 1992, we had the detection of the first confirmed planet, I'll put it that way, around pulsar B12 5712. And so what astronomers were doing, they were watching pulsars. So these are stars that flash at regular intervals. And what they noticed that every so often, these pulses would be a little bit off. And they were eventually able to discover that the star had planets orbiting it. So this was very cool. But then in 1995, we had the discovery of 51 Peg-b. So 51 Peg-b was discovered using radial velocities. So oftentimes we think of planets orbiting the star, but in reality, they're orbiting a center of mass. So the planet orbiting the star causes the star to move just a little bit. So based on this movement of the star over time, we can determine that there's a planet or another body orbiting that star. And then based on the amplitude of that movement, we can determine the mass of that object. So we were able to determine that this was a Jupiter-sized planet on just a 4-day orbit around its star. So its year was only 4 days long. And so this was a giant planet close into its star. That'll be an important part in a second. And then published in 2000, we had the discovery of the first transiting planet. So this was HD 209458. So in the transit method of discovery, this is the kind of discovery method that I use. We're looking at the star's brightness over time, hoping to catch these little tiny dips in that brightness as the planet passes in between our line of sight and the star. And so these are 2 beautiful transits. We can see these nice ingress and egress as the planet starts to cross the star and then starts to leave the star, and then the flat bottom as the planet is fully occulting the star. And so based on this, again, we're able to determine how long the planet's year is and how big the planet is. And so again, this was a near Jupiter-sized planet on, ironically, also about a 4-day orbit. So large planet, tight orbit. And these discoveries were taken very well, not only by astronomers, but by the public as well. So this really launched exoplanet science into a new wave. Lots of people are excited about it, and astronomers saw exoplanet discovery as a viable field to go into. And so this eventually leads to the launch of the Kepler mission in 2009. So Kepler's main goal was to find an Earth-sized planet around a sun-like star. And it did this using the transit method. So again, we're watching the brightness over time, looking for these little dips in that brightness as the planet passes in front of the star. And from these dips, we can determine how big the planet is and how often it orbits the star. And so why astronomers decide to use transits rather than something like radial velocities? Transits, we can stare at a lot of stars all at once, versus radial velocities, we're looking for little tiny changes, so we require much more precise data on individual stars to find those kinds of planets. So Kepler stared at a field of about 150,000 stars, hoping to find this Earth-like system. And so while Kepler, unfortunately, was not able to find a true Earth analog, it found thousands of these transiting planets. And so Kepler, for a variety of reasons, was biased against young star-forming regions. So we consider this to be the mature population of planets. So mature here being older than about 1 billion years old. For reference, Earth is about 4 billion years old. And so already we can start to see some patterns in this plot. So for one, we have a whole population of these large planets on tight orbits. We now refer to these as hot Jupiters. And so the idea that we have a lot of these is unsurprising, considering these were the first kinds of planets we were finding. But it is surprising when we take a step back and think about how these planets might have formed. So thinking about how the solar system formed, we have this nebular hypothesis theory. We start with a big giant ball of gas and dust. It collapses to form its star. This gas starts spinning up around the star to form the planets, and then eventually you're left with this solar system, this pancake flat environment. And so when the gas and dust is starting to dissipate and these planets are forming, the dust dissipates from the star the fastest, from closest in outwards. So it doesn't make a whole lot of sense that we're finding these big planets really close into the star. The material here just doesn't last for very long in order to make these giant planets. And this is true despite what radius we look at. As we get further and further into our star, so closer to our star, we're seeing less and less planets. And so this mature population of planets can't tell us how they formed. They have lost all markers of formation, and so we're left to wonder, how did these planets get here? We can play a similar game with this blob of planets here in the middle. And if I were to plot this a little bit more carefully, you would see this bimodal distribution separating out the slightly smaller, rockier super-Earths versus the slightly larger, more gaseous sub-Neptunes. And again, these old planets can't tell us how they formed. So for example, if I were to ask you to think of Earth, y'all can probably do that pretty easily. We think of this. But if I were to ask you to picture a baby Earth, a young Earth, a little bit more difficult, right? So I start to think of Pangea, but even younger than that. So this might have been what young Earth looks like at different ages. And so we learned this from being on Earth. We didn't learn this from being an outside observer. So these planets that we're looking at that are so far away, we're really only able to see its radius and its year. So we can't make these precise measurements on it. So instead, astronomers create all sorts of theories of how this bimodal distribution and this large population of planets came to be. Again, our mature planets can't tell us. These theories are designed to reproduce that population. So instead, we look at young planets. Now, I can't watch a planet form and evolve. That'll take millions of years. So instead, we create this little flip book to watch planets grow. So if we can find planets at a variety of ages, we can create an almost flip book to watch these planets grow and evolve. Kind of like you can't watch your children. You don't see their little changes as they grow up from day to day, but you look at pictures at different ages and you can very easily see them grow up. Very similar idea. And so, I mentioned Kepler. There it goes. Kepler was biased against young star-forming regions. TESS, on the other hand, TESS is the Transiting Exoplanet Survey Satellite. It is observing the entire sky. So it has observed all sorts of stars of all sorts of ages. And TESS has led to hundreds of thousands of planets, or hundreds of thousands of stars, my bad, that we can search for planets around. And so this is the population of young transiting planets that we know of to date. So in the background here, I have that same Kepler distribution, just now shown as contours. You'll notice we're missing those giant planets. This is now corrected for detection bias, so they don't pop as much as they do in the other plot. But in the foreground here, I have the young planet population colored by their age. So youngest here, and then it goes up to about 700 million years. And so we have about a few dozen of these young planets that we know of. And all of these planets are found within young star-forming regions, young star clusters. So it's very important that we look for planets around stars that are part of these young clusters because we can precisely determine their age. When we're dealing with this small number of statistics, it's very important that we have very precise ages so we can get that flip book in the right order. And so stars are born together and they travel together as they age. So if we can determine what family the star is a member of, we can determine its age based off of the bulk properties of the group, and then estimate the single star age as the group age, and estimate the planet age as the star's age. So in the new age of Gaia, we have lots and lots of these young star clusters to look for planets in. So Gaia uses the movements of stars to help astronomers determine what groups of stars there are. And so you might be thinking, so there's lots of TESS data. TESS launched in 2018. Kepler lasted only about 4.5 years, was able to find thousands of planets. Why have we only found just a few dozen of these young planets? Well, as it turns out, finding young planets is actually quite challenging. So first, this relates to all planets, but the probability that we will detect a transit is actually quite small. It has to do with how far away your planet is and how big your star is, but ultimately it's about a 1% chance that we will be able to see a transit happening. So if I was an outside observer looking into our solar system, it would only be about a 0.5% probability that we would see the Earth transit. And Mercury, which is the closest planet in our solar system, about an 80-day orbit, would only be a 1% probability. And then Jupiter, largest planet in our solar system, only about a 0.1% probability of transit. So it has nothing to do with how big you are, just how far away you are. These planets are pretty far away in comparison to their star. But then planets are just also really small. So this is roughly to scale comparing our sun to the planets in our solar system. And you can see these smaller planets are really hard to see, even just on the board. So the Kepler distribution is dominated by these Neptune and Earth-sized planets. So we really need to be sensitive down to those small sizes in these young stars in order to make comparable data sets between the mature planets and the young planets. And so again, if I was an outside observer looking in, and I watched Jupiter transit the sun, it would cause only about a 1% change in that brightness, which that sounds kind of small. I get really excited if I see a 1% transit depth. That's very clear. But again, we're trying to find these small planets. So if I were to watch Earth transit, this would cause about a 0.01% change in depth. So super, super tiny, super hard to detect. And then finally, young stars are just noisy. We can think of young stars as bouncy children. They have a lot of energy. They're flapping all over the place. So young stars can have variability upwards of 5 to 10% or more. Versus old stars, they're very calm, they're cool, and they're collected. Nice, smooth light curves. So these wiggles in the light curve, this variability is caused by star spots. So star spots are regions of the star that are cooler than the surrounding regions, and since they're cooler, they give off less flux or less brightness. And so as the star spins and these spots come in and out of view, it creates this variability pattern that we're trying to find these small planets within. So if we put all of this together, the small probability of transit, the small planets, and these noisy stars, this combined makes finding these young planets very difficult. So you can imagine if I had an older star, these nice calm stars, with these nice big planets, this is very easy to see. But we are stuck with things like this. So this is about a 100 million year old star. You can see we have this large scale variability from the spot pattern, but we also have these tiny little wiggles in the light curves as well that mimic our transit signals, which annoys me because I see a lot of false positives. I get really excited for a detection, and then it's not real. But if you were to believe me, this is actually a transit, so is that. This is about a 2 Earth radii system, so a planet about twice the size of our Earth, orbiting the star. And so these teeny tiny transits, very difficult to detect. But despite all of this, the young planet population has already proven to be very powerful in helping us understand how young planets form and how they evolve. Some of these planets have mass measurements, which are able to inform formation models, give us better ideas of what's going on. Some of them are active stars, and so we can start to study the planets around these active stars to understand how does stellar activity affect planets. And then finally, some of these transits have spot crossing events. So the planet will pass in front of one of these cooler regions. And based on those spot crossings, we can determine more about the spot patterns on stars and the temperatures of stars. So not only are these young planets informing us about young planets, but informing us about their young stellar hosts as well. But something you'll notice is that this plot is, this young population is missing any of the hot Jupiter planets. And we can begin to wonder, is that because young planets aren't in this parameter space? Do hot Jupiters form further away and come inwards? Are hot Jupiters in a form that we don't expect them to be? And then we also are missing these less than 10 million year old planets, these truly infant systems. So again, we can wonder, are they in configurations where we can't detect them, or have we just missed them? And so there's not a whole lot we can tell about this young population right now, make strong statistical claims. One thing we can start to see is that these young planets start big and then go towards the Kepler distribution. Most of the youngest planets are bigger and then seem to fall. And this goes in, folds into our planet formation theories. Planets start big, go small. But at these ages, these theories overlap quite a bit, so we can't differentiate them very well. And they also depend very heavily on the mass. If we know what the mass of these planets are, we can better determine which of these formation models they are a part of. But overall, we can't distinguish very clearly between these models at this point. And so this leads into my thesis work. So my survey is called the Tie-Dye Survey. It stands for Test Investigation, Demographics of Young Exoplanets. So the main goal of my survey is to understand planet formation and evolution through discovery of young transiting systems. So young here meaning less than about 500 million years old, though I'm right now more particularly interested in systems less than 50 million years old. And so very broadly, this is what my pipeline is. We start with test data, we go through some systematic corrections, and then we search the light curve. But going into a tad more detail, I won't bore you too much with the nitty-gritty details. But we start with TESS. So TESS is a space-based telescope. It observes sections of the sky in 28-day chunks. And from these 28-day chunks, we have different cadences of the data. So it could be anywhere from 30-minute cadence, 2 minutes, or 20 seconds. And so we really like the faster cadence data. If we could have 20-second cadence on all of our stars, we'd be super happy. It makes us just more effective at finding our planets. So we grab as much test data as is possible from our public archive, and we send it through our systematic correction pipeline. So in the default systematic correction pipeline, instrumental noise is considered first, and then stellar noise. So for old stars, this is not a problem. Remember, old stars are calm, cool, collected. So the instrumental noise being assumed to be the short period noise is fine. But in our young stars, the activity can be on timescales that are similar to or even shorter than that instrumental noise. So if we're trying to model out the instrumental noise before the stellar noise, it can get them flip-flopped. So instead, we take them into account at the same time. We model instrumental noise and stellar noise at the same time, which allows us to get these nice, clean light curves. So we then send these pretty light curves through our transit search. So this is the notch algorithm. So what notch does, it goes along every single point on the light curve and models it with a polynomial and a polynomial with this little trapezoidal notch taken out of it. And this notch represents a transit-like shape. And so for every point along the light curve, notch decides, does the polynomial model the data better, or does the trapezoid model the data better? And it gives it a score. So it goes along the entire thing. And then based on these scores, we look for little repeated dips in the scores that indicate repeated transit-like shapes, which indicate a planet passing in front of its star at repeated intervals. And so after all of this is said and done, I'm hoping to find a pretty plot like this. I'd be very happy to see this plot pop out of my pipeline. Again, we see that nice, pretty sharp ingress-egress, and nice flat bottom as the planet is going across the star. And so here's an example of our pipeline with our extraction pipeline with our search pipeline in comparison to the default. So the purple is our custom extraction versus the orange is the default pipeline. And already in this raw data, this brightness over time, we can see our purple light curve is nice and cleaner. And then we send it, this is after we are detrending it, so after the polynomial passes through. And then here's the phase-folded light curve. Phase-folded, so I'm cutting the data and stacking it on top of each other, stacking all the transits on top of each other. And you see in our purple, we have this nice transit shape, versus in the orange, we don't see it at all. So our custom extraction plus our search algorithm is able to find these smaller planets that weren't able to be discovered before, which is very cool, very exciting. So that's the idea of what my thesis is doing. And so we started by looking at some of the youngest clusters in the sky. So one of the first clusters we looked at was the Taurus-Auriga molecular cloud. So Taurus itself is made up of about 16 distinct subpopulations, ranging from about 1.5 to about 15 million years old. And part of the D4 North subpopulation, we identified target IRAS 041252902. You can call it Tie-Dye 1 if you want to. So Tie-Dye 1 is an M0 pre-main sequence star, and it has an age of about 3 million years old. So we get this age in part by it being part of that D4 North subpopulation of Taurus-Auriga. Previous studies have put that population at about 2.5 million years old. Our analysis of the individual star puts it about 3.3, so about 3 million years old. So this is an M0 class 2 star. All that means is that the star is done forming, and the material that formed the star is starting to dissipate. It dissipates inside out, remember that nebular theory, and it creates this ring-like shape. And in fact, if we look at previous data on the system, we see this near face-on disk. This is SMA data, and we find that it's about 30 degrees from face-on, so just tilted a little bit from face-on. If you're a more visual person like me, this is more in line what you should be thinking about. So we don't think this blobby shape is a true characteristic of the disk. It's more likely has to do with the quality of the data. So these are similar transition disks from ALMA, which is a higher resolution instrument. And you can see these nice donut-like shapes. Since we submitted our paper and since its publication, there has been ALMA data on our system that has been taken and made public. And I Haven't reduced that data myself, but I took a quick peek at it, and we do see this nice round donut-like shape. So consistent with these sorts of images that we were seeing. But normally, if we are seeing a disk and we're looking for transiting planets, this would be a cause of concern. So when we're thinking about finding a transiting planet, there's an expected geometry for our system. So we're expecting the star to be rotating edge-on, and this planet to be orbiting edge-on as well. So thinking back about planet and star formation theory, if the disk is still present, we're expecting it to be in that same plane of rotation, so blocking the star and blocking any hopes of seeing our transit. So even if the disk is face on, we're then expecting a polaron star and the planet to be going around the star. But our analysis of the system suggests that the star is actually rotating edge-on, and this has given us the perfect window into the star to discover the transiting planet. So Tidai 1b is about a Jupiter-sized planet on an 8.8-day orbit around its host star. So this planet was discovered using 6 sectors of test data. And the first sector was taken all the way back in 2019. And you can look at this raw light curve, and you can see it pretty well in the raw data. So it's not necessarily that this planet was hard to find, more that there's lots and lots and lots of stars with lots and lots of data that still needs to be weeded through. And so we were able to determine that this is about a Jupiter radius system planet, and then we put an upper mass limit of about 0.3 Jupiter masses. So you might be thinking, like, this seems very off. So this large radius but low mass is actually in line with some of the other young planets that we were seeing. We think that this planet likely has a very large atmosphere that will blow off as it gets older, but that's what's causing this puffy nature. And so once we detect a planet, we have to confirm it. We don't want to look silly and call another star a planet. So one of the first things we do is take additional transit in more wavelengths from the ground. So there's a few reasons that we do this. So for one, TESS has a very large field of view, very large pixels. So there sometimes can be multiple stars on one pixel, and it can confuse our extraction algorithm what star is actually being pulled from. So if we can take a transit from the ground, we can have a smaller aperture that just looks at our one star, so we can confirm the signal is coming from the star that we think it's coming from. But then we take it in multiple wavelengths because we want to ensure that the transit is the same depth across different wavelengths. So stars emit light, and they emit light, different amount of light at different wavelengths. So if this were a star transiting another star, we would see these different wavelength transits have different depths. But since a planet is a non-emitting body, it should have the same depth across wavelengths. And so the fact that we see all 4 of these wavelengths have the same transit depth, that's a point for this being a planet. We do a number of other follow-up observations as well. So for one, we look at radial velocities, so remember that movement of the star over time. And using just 6 points out of HPF in McDonald in Texas, we're able to put an upper mass limit on the planet of a 0.3 Jupiter masses, but we're also able to use these radial velocities to rule out a stellar mass companion. So using archival radial velocities mixed with our new observations, we're able to rule out anything greater than 2 Jupiter masses, which strongly rules out anything star mass sized. And then finally, we look at imaging, so literally pictures of the sky at different times. And what we're looking for here is looking for any stars that are coming in or out of view that might be a binary system that's imposing this transit-like signal onto our star. But across this time, we can see that the star from 2009 to 2023 moves quite far in the sky, and no stars come in or out of view. So this likely means that this is the only star there. So we find that this, again, another point for being a planet, and we're able to confirm the signal as planetary in nature. We also find that the system has a wide binary companion, and we originally believed this star was the cause of the disk becoming misaligned. But we did further analysis on its orbit, and it seems that the orbit is in line with the planet's orbit. So same inclination as the planet, so unlikely to have caused this disk to warp out of the way. So this is a really low mass star, only about 0.2 solar masses, and it's on a 600 AU orbit, so 600 times the distance between our Earth and the Sun. Our planet was orbiting at about 0.1 AU, so super, super far away from the planet-star pair. So overall, we see that we have a rotating star, an orbiting planet, and an orbiting star all in the same inclination, which is highly misaligned in comparison to the protoplanetary disk that form the star and planet pair. And so already the system is proving to be very valuable in our understanding of how planets form and linking this idea of how planets form in the protoplanetary disk and these super young transiting planets. And so that makes TIDI 1b the youngest transiting planet that we know of to date, and the only transiting planet known to be in the presence of the protoplanetary disk that formed it. And so because it's so young, it's about 3 times younger than the next youngest planet, which is about 11 million years old. It's becoming a very valuable system for follow-up data. And just for a comparison, again, if Earth is 4.5 billion years, if we consider it to be a middle-aged person, this planet is just 2 weeks old. So a super-duper baby planet in comparison to everything. And so for the last little bit here, I wanted to talk about some things that I'm excited for with the system and what the system might be able to tell us. So I kind of threw up some of these formation models earlier and kind of as a throwaway. But because TIDI 1b is so young, we're actually able to catch it forming and directly test these formation models. So these are 2 models of formation that we are thinking about right now. In this top one, we have a high mass core that grabs on an atmosphere really quickly and then very quickly blows it away. So we're left with a cool planet that is very massive. Versus in this bottom path, we have low mass core, and it slowly builds its atmosphere over time. And so we're left with a hot planet with a low mass. And like I said before, these formation models are tuned to reproduce this Kepler distribution. So even the slightly older planets, those 10 to 100 million-year-old planets, we couldn't test these formation pathways. But IRAS, TIDI 1b, is so young that it's in the middle of these formation. So if we can get a precise mass measurement on the planet, we can directly probe which formation pathway it's a part of, which I think is really cool. So normally, masses for young planets is pretty difficult for the same reasons that it's difficult to find these young transits. Young stars are just noisy, so it makes taking the data very difficult, especially for radial velocities. So instead, we're very excited about JWST. JWST is able to probe the atmospheres of young planets through what we call transmission spectroscopy. So based on the composition of our atmosphere, the planet looks bigger or smaller in different wavelengths and creates these features in our depths. So I lied just a little bit earlier when I told you that when we're looking for transits, that they're the same depth at all wavelengths. That was a little lie. It's true in optical wavelengths, so where the wavelengths that we're able to take from the ground, so it's fine. My little white lie was fine. But as we get into longer wavelengths, we see massive differences in these transit depths. And this changes as the mass changes. So this method of finding planet masses has been done already. So a recent paper out of our group by Pachia Tao looked at the mass of HIT 67522b using JWST data. And so previously, that planet was considered to be a hot Jupiter. It's on about a 7-day orbit and has a radius just shy of Jupiter. But the mass measurement she was finding was more like 15 Earth masses. So it makes that much more likely to be a precursor of the much more common sub-Neptunes and super-Earths that we're seeing in the Kepler sample. So these puffy planets losing their atmospheres. So I'm very excited to learn about this. I'm very fortunate to be part of a JWST proposal that was approved for this upcoming cycle, probing not only the planet's atmosphere, but the disk composition as well. And one goal of that survey is to understand how those compositions are similar or different. And then our planet mass, of course, we're going to get and be able to test these planet formation models. And so I will throw up my conclusion slide. So if you have any questions that you might think of later or I might not be able to get to, feel free to email me. And if you're looking for the nitty-gritty details of our paper, if you want the exacts of it, this QR code will take you to the paper that we recently published in Nature at the very end of last year, describing the discovery of this system. Thank you.
So if you have questions, if you would, Madyson, repeat the question. Questions?
What could cause the dust disk to be so inclined if it's not the companion star?
So what else could cause this disk to warp out of the way if it wasn't the star? So I'm not a simulation person. I'm waiting for the simulation people to tell me what they think caused it. Right now, we think it's probably some sort of flyby that happened during formation.
What would be your reasoning for why a planet so big and such a
So why does such a big planet have a tight orbit? So that's a great question. So the planets that we discover are limited in period space because of the cadence in which we take data. So we're limited in finding planets that are closer into their stars. But why they're there in comparison to our solar system is a great question. We're still trying to understand. Yeah, I don't know. So all the planets that we're finding are interior to Mercury, which is the closest planet in our solar system. Yeah, I don't know if it's because our solar system is just different or what, but right now we're biased towards finding these closer in planets.
Yeah, I have a question. Because my question is, we talk about the rule of binary system. But how about if the system, like the solar system, there are multiple planets, especially for early stage, so the orbit is not fixed. Somehow there will be chaos in whatever. Those things also can impact your observation, because your observation basis on the intensity, right? If there's another young stage of planet or small, so it run each other. So how do you rule out that possibility?
So how do we rule out other planets in the system?
Maybe multiple planets that in the system.
Yeah, so if the planet, so for us to be able to see a transiting planet, it has to be in a very particular range of inclinations. So we're able to rule out, at least not in, from my search, we didn't detect any other transiting planets. What I'm interested in is to see if there are any planets in the outer disk, so in the warped material. I don't personally work on directly imaged planets, but this is something that other people are starting to look into to see if maybe there are planets on other inclinations in the system as well.
Because it's so much fun. I think we observe the pattern is different pattern. One pattern, another pattern, very consistent with each other. So maybe we can do other stuff. Because we can be sure, so maybe it's only young stage of the planet. So we observe that because more stable pattern, if we have other planets, we not stable. So this time we observe this kind of small change. Another time we observe the change, then we simply think about this is my guess.
Thank you.
For all the exoplanets you talked about here within our galaxy, or will some of them have life?
So are all of the planets that we're detecting inside of our galaxy? Yeah, the stars that we can detect planets around are pretty local to us.
Okay, and my second question is, just based on your experience, do most stars have planets, or do most stars not?
And then the next question was, do most stars have planets? So that's also part of my thesis work, is understanding the occurrence rates of planets around young stars. So we're finding for mature systems in Kepler's occurrence rate is about 0.7 planets per star. So about 70% of stars have planets. And early work looking at less than 200 million-year-old systems by Sidney Bach shows that the occurrence rate is slightly lower than that. So trying to understand how do occurrence rates change with age, and how does that fit into our formation and evolutionary models.
So I actually have two questions. One, has, in the disk, have there been radial velocity planets detected so far around other stars with disks? Or would finding one around Tidai 1 be the first?
So are there radial velocity planets around stars that still have their disks? Not to my knowledge. This is the first transiting planet with a protoplanetary disk. I think the only other planets within protoplanetary disks are directly imaged planets, which tend to be very large mass planets very far away from their stars. So I don't believe any radial velocity planets have their disks, but don't quote me on that. I'm not super sure.
The other question is, you said there's about 0.7 stars, or 0.7 planets per star. Is that accounting in some way for the observation bias, or is that just in terms of the stars that we've looked at? That's how many planets, or that's how many planets are on each star?
Yeah, so is the 0.7 taking into account detection bias when looking at the occurrence rate per Kepler planets? So that is folding in everything, like no matter the inclination, there should be, on average, 0.7 planets per star.
So like even if it's like a planet that like a Jupiter that we can't detect because it takes too long to orbit, that's accounting for that. Okay.
Are there any plans to search for planets with longer orbits?
So as we can get more test data, we have longer and longer baselines, which enable us to find longer planets. So my cap is about 50 days, no matter what system I'm looking at. But as we get longer and longer baselines, we're able to look for longer and longer periods. Where do I see the young exoplanet field going in the next decade? That's a great question. I'm very interested in, so JWST is relatively new in probing young atmospheres of young planets, and this is starting to get our first look at the composition of young planets. So when I was talking about we were seeing the different Earths evolve over time, we were able to start thinking about compositions. When we're looking at transits, we don't get that information. But using transmission spectroscopy with JWST, we start to piece together new information. So that's very exciting. Also, the Habitable Worlds Observatory is kind of the next step in that, trying to find Earth-like planets that might be more Earth-like, livable, habitable, if that makes sense. So those are the next few ideas that are coming along. So what follow-up studies am I most excited about for Tidai 1b? So of course, the JWST data that's getting taken on it, I think that's very exciting. We're also starting a new survey looking at the planet alignments over time. So if we think of our solar system, all the planets are pretty much in the same plane. This is not true in the Kepler distribution of planet alignments. We see a large range of alignments and misalignments in comparison to the rotation of their stars. But we see that the young population so far in our few data points seems to be very aligned, still very pancake flat. So we're trying to figure out at what point does that turn off happen? And so therefore what mechanisms cause these misalignments? So we're starting to look at that with our system as well. That's one of the ideas we have. So there's just lots and lots to do on this star and this planet. And I'm very interested to see how we're able to link the disk people and planet people and stars people with the wide binary companion. Everybody starts to collapse onto this one system. And so I think that's very exciting as well.
Okay, one more here.
I was just curious as to like if you found any exoplanets like outside of our galaxy that we studied so far.
So have we found any planets outside of our galaxy so far? So we haven't yet. I think with surveys like this, when we're looking at the brightness of the star, other galaxies are just too far away to see individual stars to be able to do this kind of work. But yeah.
Let's thank our speaker again.